Okay, so let's get started here. So hello everyone. First of all, I would like to thank the BSidesPhilly committee for inviting me here to talk. And I would also like to welcome all our audience here for this presentation. And today I'm going to be speaking on how I found the ICS data during my internship. So a bit about my background before getting started. So my name is Shail Patel, and I'm also known as BNTCV, and I'm a security researcher and an application security engineer at Forum Assembly. Previously, I have also worked at NREL back in 2019. There, I focused on the ICS and SCADA security. I've been in cybersecurity space for about 2 years now, and occasionally I like to participate in vulnerability disclosure programs, bug bounty programs, and I also like to do CTFs. So the first of the presentation was a part of my internship research from over a year and a half ago, back in 2019, as I mentioned. So while I was interning there, this was performed in a controlled laboratory setting with all kinds of capabilities. So now the project team has devised data enhanced hierarchical control architecture. So this DEHC architecture was developed to solve some unique power system challenges such as feed load balancing, reverse power flows, or voltage stability. So with that in mind, I performed the testbed security assessments from various perspectives, including the communications in transit, site-specific device level security assessments, and vendor device security analysis as well. So the last half of this talk will be focusing on the notorious findings in the wild that I did for just fun and just for educational purposes. So let's get started here with the basics of industrial control systems. So in simple terms, industrial control systems are basically the computers that control the world around you. So they are responsible for managing the AC in your house, or maybe in your office, or turbines at the power plant, or an electric power grid. So there are some various examples of industrial control systems. So some common terms associated with the ICS are PLCs, programmable logic controllers, distributed control systems, remote terminal units, and HMIs. So these are the various entities involved within the ICS. So now, before diving deeper into specifics, it is really important to understand the difference that operational technology, which is OT, systems vary in a lot of aspects than traditional enterprise IT-based implementations. So the way it works is operational technology monitors and manages industrial processes, assets, and manufacturing. So essentially, it's a hardware and a software that keeps the industrial systems running. So I would say that a common way of looking at the security requirement of an IT system is to acknowledge that it's data-centric. So the key requirements being the confidentiality, integrity, and availability of the data being processed. But for operational technology, for OT systems, let's say that an attacker might be able to see the furnace is on or off, or at what temperature is your, the AC is operating isn't really a concern. So, but hey, what if there is no availability of power supply? So just imagine that we are in the middle of the winter and there's no backup generator, which is, even if it is there, it is compromised. And let's say the grid is compromised. So what do we do in that case, right? So there are some safety concerns as well that we are going to be talking about in detail associated with that thing. So for another reason, OT is less concerned with data and more concerned with physical processes that I mentioned. So the primary concerns of OT systems are reliability and safety. So it is important to note that not all the IT security testing methods and common findings and recommendations can be reused in the OT space as well. But I'm very sure that I'm going to be talking about a lot of overlaps as well along the line this presentation down there. So it is important to note that organizations leverage lessons learned securing enterprise IT, but they also adapt those lessons to the unique characteristics of OT. So now everyone is well aware of the Ukraine grid attack example back then in 2016. So this includes moving beyond the perimeter-based security in a facility and then adding security controls to the assets that matter most. So let's talk that thing that ICS cannot be easily taken down for security updates, and so often they therefore remain vulnerable and unpatched. So furthermore, because the systems have very limited computing resources, right? So they often lack the capacity to run anti-malware softwares and various kind of monitoring tools and devices. So, but in recent years, operators of the critical infrastructure have increasingly deployed recommended technology controls for protecting their systems, but there are not enough people to man them. So there is a shortage of enough people to back up the ICAs. So another thing is that if we don't have any clear visibility to figure out what we have installed in the field, and basically we are dead in the water, right? So biggest mistake that is being made is comparing IT security with control system security, but they are still fundamentally different, and there are also overlaps as we are going to be talking about them in detail. So regardless of our experience, no matter how well trained we are, we all make mistakes, and it is okay. But sometimes this human mistakes leads to severe consequences and causes harm. So in order to avoid this, implementing industrial control systems was essential. But later we realized that this industrial control systems, this itself has its own problems. So now, in this project had hardware in the loop setup in the test bed with different devices interconnected in the ICS topology. So now, hardware in the loop was implemented for the development and testing of this complex power system here. So basically, our task here was to capture the communication between the Beaglebone device and the PV inverter. Now, PV is nothing but photovoltaic, anything that is to do with the sunlight. So note that the communication protocol used in this case is Modbus. So Modbus is an ICS protocol, as I mentioned earlier. So Modbus runs on default port, which is 502. So in this case here, we are capturing the Modbus traffic between our Beaglebone device and our photovoltaic inverter. So, but before diving into the details, there are certain things to be taken note of, like say for instance, Beaglebone. It acts as a local controller for stabilizing the inverter set points. Now, unlike TCP/IP and UDP, Modbus is a communication protocol, as I explained in the earlier slide. So it's extensively used in the SCADA systems, and which was also used in our case. So Modbus serial protocol is nothing but a master-slave protocol. Now, one master control Modbus data transactions with multiple slaves that responds to the master's request to read from or to write the data to the slaves. So there are various read-write and operations that can be performed within the Modbus topology. So it's also important to note that anyone can implement Modbus in their field device architectures, and since it is free and an open standard available. So now each device communicating on a Modbus protocol is given a unique address. So as you can see here on Modbus RTU, so there are two types of Modbus. Modbus RTU is nothing but Modbus remote terminal unit, and another being as Modbus TCP/IP. So in this case, only the Modbus RTU can initiate a command. So it's always the case that, okay, the master is listening to the slaves, and slaves are sending or asking for some requests. So whereas in this case of Modbus TCP, any device can send out a Modbus command, and thus they can act as a master. So, but as I mentioned, although normally just one device acts as a master. So with that in mind, we can say that, okay, we are initiating the request here. Okay, so Modbus is we have the master and we have the slave. So to the master, we are initiating all the commands to the slaves, and in that the action is performed to the receiving response side for the Modbus for the master. So within the function code, and also it has a data response. So the slave has a specific format, just like a header, and we have PDU, that is packet datagram. So in this case as well, we have function code and data response, which is sent back to the master. So we have to note that read only as well as read write operations can be performed on the input sets. So as you can see here, that Modbus commands can be instructed to change the values in one of its registers which is nothing but writing to the coil and holding registers. And it can be also used to read an input port to read the data from a discrete and coil ports. So you can see here there are 4 types of functions here. There are various use cases here that we can use for read-only, read-write, and we also have the bitwise operations that can be performed within the object types. So within this table, we can see that to command the device to send back or one or more values containing its coil and holding registers. So Modbus can be used for multiple purposes within the registers. So the command contains the Modbus address of the device it is intended for. So just I mentioned a few slides back, each Modbus has its own device address. So about Beaglebone, it is nothing but a low cost and low power open source development platform for running and creating your own experiments. So this Beaglebone here was programmed by the power systems team to control the photovoltaic inverter. So for the purpose of simulation in the testbed, they had 2 things in the loop. So one of them being OpenDSS, which is nothing but distributed power simulator, which was used for grid modernization. And another thing was Opal RT simulator, which we are going to talk about in detail in a while. So now inverter was used for converting the direct current into alternating current. And in this case, we also used for continuously monitoring the grid for optimizing the power along with the active and passive monitoring of the controls for temperature. So there are various things that are going with the inverter as well. So now that the testbed is set up, all I did was I was in the lab. So I jumped to the same subnet and I used the network tabs from with multiple monitor ports for monitoring the Ethernet links. So you can see here that DualComp is a company and it manufactures network tabs that we can use for plug and play in the network. So now once I was connected to the network, then with the help of Wireshark, I filtered out the protocol, which was Modbus in our case. So I quickly filtered out Modbus in our case and allowed the packets to be captured simultaneously through the tab. So here you can see that all the communication that happened between our Beaglebone controller and our inverter is disclosed in the plain text. So this is nothing but the PV set points. The photovoltaic inverter has its set point values from the coil register. So this is not nothing but the values from those register. So now we got what we need. So what we can do is, with the help of this tool called CAS Modbus Scanner. So Chipkins is a company which makes this tool to play around with the Modbus values. So we can perform false packet data injection, play around with the values, and we can read write and we can manipulate the coil values as well. So note that they support both the Modbus methods. So serial Modbus RTU as well as Modbus TCP, which was used in our case. So all you can do is you can quickly provide your target IP address here for Modbus protocol. Of course, it's a default port 502, and you can connect to their Modbus system. And of course, this is a remote connection, so you have a long-lasting stability. So we can start discovering every detail from within this, such as register values. So this is some kind of a confidential information that Modbus register holds the addresses. So we can start looking for such register addresses to discover for. And another option it provides is for polling. So Modbus polling allows you to monitor several slave devices simultaneously, so which is indeed a time saver. So with the help of Modbus polling, we can monitor all the slave devices together, and we can save time with that. Yeah. So another thing is another tool that is being used here is Leva Modbus. So this is also used for polling, but from the previous finding here of our register values, all we can do is we can input the IP address here, and we can also provide the register address from the previous finding here and connect to the list of all the slaves and just passively sniff through all the traffic and listen through all the slaves. So yeah, there are some amazing functions that this tool provides for monitoring the network traffic and as well as changing reading as well as writing the data to the registers. So another interesting packet capture scenario here was sniffing the SIM and UDP traffic. So SIM is nothing but computer integrated manufacturing. So this scenario consisted of RT-OPF, so which is nothing but a short Python code for setting up the power flow balance equations, voltage as well as the load parameters. So this Python script holds various voltage values as well as power flow equations values. So unlike Beaglebone, RTAC is nothing but a real-time automation controller. It's an automation platform which was used in our case to act as a PV controller. So this was used as a photovoltaic controller for connecting to the other substations, which sends command and control to the field devices. So RTAC is different than RT-OPF, which is also different than the inverter. So all these devices are performing different functions and each hold own unique values and confidential values that we can look for. So in this PCAP here, if we pay close attention to any of the response packets, you can see that there is a 24 bytes data string here. So that kept me thinking, this is the string that we should look for. So what I did was I further followed the streamline from the settings, and I found that one of this hex string and another was a binary stream. So I know that there was some juicy data hidden behind this. So binary stream was nothing but a clear text stream. So there was no decoding of any kind. So I did not have to use any kind of decoding tool to find is there any hidden data behind it. So that was just for the clear text stream that I found for. So now another thing that we can look for is for the hex stream, all I did was I converted the hex stream to the Little Indian format. So this can be done with any online utility or any other tool that you can look around for. So this were nothing but the analog decimal communication values here that were used between our RTAC and our RT-OPF that we were looking for to test. So this was an interesting use case scenario where we were able to dig up some analog values that were used in the communication between our RTAC and RT-OPF. So one of my favorite ICS protocol is DNP3, Distributed Network Protocol, and DNP3 runs default on port 20,000. So the communication is completely in plain text in case of DNP3. So no need to worry about register calls and input values. So all we can do is just read and read directly, which is different than Modbus. So an important thing here to note is for ADMS, it is a software platform, Advanced Distributed Management System. It supports distributed management and optimization, such as finding fault location or isolation, as well as restoration, right? So while we covered RTAC already in one of the previous slides, so we can keep moving forward with another finding. So what is the data that we are looking for here within this screenshot? So within this PCAP filter, all I did was I looked for DNP3. I filtered the packet for DNP3 in the results. And in the request response here, we can see zeros and ones as binary streams. So these are nothing but capacitor bank values disclosed when our RTAC and ADMS are communicating. And another set of values captured from the same test are RTAC values sent to the ADMS in either volts or kVAR, which is nothing but kilovolt amperes, which is a reactive power as well as a unit of capacitor in our case. So just like Modbus, we can perform spoofing attacks, false packet data injection, or replay attacks, or we can also manipulate time synchronization. But unfortunately for me, none of these DNP3 based attacks were in scope for me for testing. So now I have completed the packet capture analysis. Now it's time to move on to the device level security assessments. So in order to test the Beaglebone, I ran the device through some open source vulnerability scanners. I ran the device to find some open ports and services associated with that. So I did some dynamic analysis. I also ran it through Nmap. I ran it through Sparta and observed some interesting results. So some of the open ports here were DNS, which was on 53, Node.js running on 3000, and some unessential services which I was not interested to look for. So it also appeared that one interesting thing was Cloud9 IDE. And when I checked that repository, it appeared that it had no authentication. So I could quickly get into the Beaglebone environment and hit the web interface, but just by going to the web panel. So it was totally lacking authentication, and which allowed me to read all the image data within down this image. So also I noticed the outdated version of Apache here, and it also had the directory listing enabled on the root directory that allowed unauthorized listing of files and directories listed on the image. So I ran it through various tools. I checked for various indexes. I checked for directory indexing, and I found out that, yeah, it was a missing parameter. And so I confirmed that manually. And since OpenVAS is no longer a maintained project, but it was one of the good tools that discovered shell shock vulnerability in my Beaglebone environment. So shell shock happens when you're running older versions of bash, which are vulnerable, and that allows arbitrary code execution. So after enough of findings, I ran the Apache and shell shock proof of concepts to measure the impact, what happens in the Beaglebone, and it was a successful pen testing. So I reported that to the team, and they applied the fix to that thing. So another in-scope assessment for me was for checking the RT-OPF Python code. So since this was in Python, and it was allowing me for static analysis, so all I did was I ran this through various tools like Bandit, DLint, Prospector, Prelint, and since this was short and sweet and simple code, so and it was under development, so this limited my testing techniques for source code review here. But this code nothing this tool is nothing check for source code redundancies. So in our case, nothing was discovered from security perspectives except for white spaces and indentation problems, which was a normal expectation. So moving on to the vendor device security assessments, there were lots of pieces involved, and I'm not going to name specific vendors here for obvious reasons. But Grid Edge Management System, which is nothing but GEMS, it's a web portal that can be leveraged in different ways for field device control and data visualization. But since cryptographic attacks are very omnipresent since quite a long time, so I checked for the OpenSSL version. It was running on the outdated OpenSSL version on this platform, and so I was able to find out hardly proof of concept from this link, and I ran the exploit and it worked. So I was able to confirm Heartbleed attack within this utility, and I reported it to the team. So another utility that I was testing was Advanced Distributed Management System. So while auditing ADMS software, I can relate the flaws from our packet capture scenario. So there are no signs of encryption here. There is nothing such as there are no signs or there are no tools or import functions for cryptography. So as you can see here, either while feeding the electric values here or either while data is in transit for DNP3. So distributed approach for ADMS management would have been a better approach than this for managing these assets instead of centralized management like this in terms of security. So yeah, that was an understanding. So another day, another assessment, but this time I did recon on the inverter, but did not find anything concrete that I was looking for. So the next thing that I did was I scanned the whole subnet for this test bed. So for asset discovery, I found the web interface for inverter's cluster controller. So this was nothing but the HMI, which had a prompt box for 2 default users. So I got excited. I had default users. So immediately I looked up for the datasheet for this model, and it had default credentials user 0000 installer 11111. So I immediately entered one of these credentials, and while finger crossed, it fortunately got me in. So once again, I had a complete control over the HMI that not only allowed me to view the power plant information, but it will also let me edit instantaneous values and change some of the privilege settings within this panel. So yeah, there are some fun stuff that can go around with this panel here. So last year as a red team lead, I was involved in building and creating vulnerabilities and exploits from scratch as part of one of the cybersecurity defense competition for students. So my job here was to help the red teams achieve their goals. So in various scenarios here, I misconfigured Raspberry Pis. I left the HMI for one of the solar panels unauthenticated on the box. I enabled Django default. I ran the cron jobs to reset the firewall connections, implemented sticky keys vulnerability. I left the FTP server open and guest users enabled. So basically think of any system, network, or application level flaws that will help the red teams for exploitation. So but my most favorite thing here was that I wrote a logic bombed backdoor in Go to spawn a reverse shell in one of the HMI boxes in the middle of the competition to create chaos. So what this backdoor did was it opened up random ports at specific timing. So as soon as there was a competition time, boom, 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 it opened all of the network ports, and with the help of that, red teamers can connect to these ports and they can have access to the backdoors. So the proof of concept was also available on GitHub if you want to check that out. So enough of the serious talk now. So from now, the later part is more about my finding in the wild using Shodan. So as most of the people must be already familiar with Shodan, it's an IoT search engine where you can find any specific model devices, including endpoint devices as well as servers. So you can literally search for anything on Shodan. So Shodan is available in free version as well as it has its paid features. So some of the good people here are from SCADA Strangelove group, who keeps on posting the SCADA devices on the internet as assets. So one might want to check that out as well. So now the way that Shodan works is it's also similar to Census, which is also another spiraling engine. So all they work is by spiraling all the IPv4 addresses and maps all the banners and host names and other records to that particular IP addresses. So you can also do targeted search for CVE addresses or ports and services for a particular target on Shodan. But apart from direct search, Shodan also provides API version to search with command lines. So the interesting thing that it allows you to check live state of the device, so you can filter out quickly on what to focus and what to not focus. So it clearly shows what is the device model and from what organization or company. So there are some fun findings that I'll be presenting in coming slides for default credentials. And along with the banner state information, the search will also show you the configuration parameters for certain types of services. So it can help us in finding misconfigurations in this particular case. Now, many domains and subdomains have literally no authentication, where you can visit them on the banner, which you can see in a few examples in the coming slides. Now, this is an obvious statement here. So the more you recon, the better are your findings. So you can use Google as well as Shodan and all the other types of search engine down the road. This is a perfect example of no authentication, where Shodan offered me this electrometer. So if you have a close look at this HMI here, you will observe that this meter has a lot to offer. Now, you can read the voltage, all the power related information. You can check the status of the substation here from the settings, and you can do many more fun things. So yeah, this electrometer was openly available on Shodan without any authentication here. So this is a particular thing to take a note of. And I also looked for network components such as routers that were openly exposed on the internet. Now, there's a login page for Sierra Ace Manager router. So I did was I entered username user and password 12345, which were the default credentials. I just guessed it and it worked out. So now if it is a router and you're logged in, so you can know that the quality damage that you can do at layer 3. So you can change the IP addresses, network addresses, break the connections, disable network authentication, and basically you can destroy the whole network. There are multiple default credentials available online for this particular model, but since it was allowing me to log in with user and 12345, so I did not look any further. HP printers are very interesting things to look for. So again, it did not ask me for any login information. You can check the device state here. You can check that from the configuration settings. You can check the usage, event logs, who printed what, at what time. from what printer. So all the metadata that we call it, we can fetch along from this machine model. You can also give the print commands anonymously and just print and waste the whole cartridge, right? So that is something that that can also be used by an adversary. Now, another HP model, but same old mistakes here, zero authentication. Now, if I was a bad guy, like I mentioned earlier, I would have emptied the whole cartridge and printed random pages and changed the access control by kicking the admin out. I would have done some exfiltration, get to know the printing history for their important documents. Now, it could be anything from pay stubs till any private employee information, which can be stolen easily and quickly. So there are many fun things you can do here and mess around with them within the printers as well. This is a controller unit from Endorx company that runs on IEC 60875, which is a common transport protocol standard for power systems automation. So here I did a reverse lookup for this standard on Shodan, and it brought me up here. Now, again, there was no authentication here. So it's even scarier here since it allows unauthorized file upload here, as you can see, to this HMI. So this is a serious issue. Now, I could have uploaded a backdoor or a ransomware. It also displays the firmware version here. So an adversary might also look up for a known proof of concept here by checking the version number. So this is a COBAM satellite, which you can see here, and it has an active slay here. So you can also observe that it has received and transmission signal strength here. So you can see that it has an active received strength as well as active transmission strength. The dashboard gives a variety of satellite parameters, such as where it is located, frequency, elevation gain, antenna information. You can also go to the settings and manage the administration, and you can also change the admin access. So if satellites are compromised, then chances are, yeah, the space technology is going to be ruined up in the future. So this is another thing that needs to be taken care of in terms of IoT and ICS exploitation. This is a live solar log inverter in production, which is exposing the network, device configuration, system, and plant details. This is almost everything to spill out the beans for. So the next time when you see this device by yourself, you need to know what kind of exfiltration techniques that you need to apply to extract the data out of this model. So yeah, an adversary can research this model and then look for detailed parameters to further exploit it. Now, this is the Tesla's Powerwall battery for controlling, monitoring, and optimizing, which is showing an active status here with load unit measurements. Now, isn't it fun to read someone else's battery status and measurements? So this is displaying everything like battery status, how much power, how many horsepower, how many kilovolt ampere, at what kilovolt is your battery running, how much percent is remaining. So an attacker might have some fun by modifying the parameters or might further brute force the directories and look for more information from this. Now, these are unauthenticated webcams from houses, schools, or localities. It can be from anywhere. So on the bottom right here, this is an HMI for the Wind portal. Now, this was the only HMI amongst all my findings where my default credentials did not work, but it allowed me to fire up some XSSs. Now, this could have been further utilized by me or any adversary for credential stealing or cookie stealing with XSS. So what does this all imply here with all this everything? So they just want easy access to get in, and they did not bother to change the credentials. So therefore, there was no authorization. There was no authentication of any kind except for local backups. Now, you don't need any fancy scripts or frameworks for finding sensitive information. You can just go to the Shodan or any other search engine and do open source intelligence and find some sensitive information like this. So all these instances should not have been openly available on Shodan or any other search engines as well. But like I said earlier, it's the laziness that is thriving. happens on accident. So every day on Twitter, I read someone finding GitHub or AWS secrets or keys and whatnot. Now, this is something that is not done accidentally. Now, as developers, we are just lazy. That is why hard-coded information is easily available there. Now, security through obscurity is nothing but hiding the underlying security mechanism. Now, even if you are hiding your security mechanism, that won't help you at all in this case to protect these devices, because people are smarter. They will find alternatives, and yeah, they will dig up, and then they will use all the exploitation vectors and attacking techniques that they gather, and then launch all the attacks. So it also appears that there were no firewall rules that were implemented to block these connections from accessing these devices remotely. Now, of course, I cannot stress enough the importance of the word default. You have already seen it by now. And of course, this devices should not be there on the internet, right? So there is no harm in implementing Modbus if it is done correctly, but no plain text. So regardless of serial Modbus RTU or Modbus over TCP/IP, I suggest that add an extra layer of transport layer security, TLS, for encryption. And UDP itself is unreliable, but even if you're moving forward with UDP and if you have sensitive information, you can use secure protocols like DTLS, Datagram Transport Layer Security, for maintaining the privacy. Now, like Modbus, do not just use default DNP3. Instead, use the newer implementation, which is nothing but DNP3 Secure Authentication, DNP3 SA. So this DNP3 SA will provide role-based access control, authentication, and authorization for these devices. So check out the new version for DNP3, and I think the newest version is version 6. And another interesting protocols that can be implemented for additional security or either as a replacement for D3 are SEP2, which is nothing but Smart Energy Profile, ICCP, IEC62335. But again, it all depends on your applications and needs. So you might want to work that out with your developers and your power systems engineers, and then decide the protocols that needs to be implemented. And same problem here. They could have firewall Beaglebone. They could have disabled unnecessary direct listing. They could have patched the known vulnerabilities. Now, vendors make mistakes too. So that's why vulnerabilities is a serious trouble in some cases. Now, so that's why you don't want to read more than what you're allowed to from the memory. And so I'm glad that the vendors fixed this problem. Now, it is important to take other defensive actions other than having a barrier of networks, like in this diagram, to control what is flowing through locally and externally. So most of the people are focusing on enterprise level security now, but we also need more people in ICS security as well. There should be an equal distribution. There should be equal distribution of manpower. If you are a power systems engineer, it is essential to know what you are placing in the production field. It is if the device is not needed anymore, disconnect it from the internet and take it offline before you forget. So we cannot just be like, hey, I had my PLC in the field and I just found out today that I cannot log in, and they are just compromised. So yeah, just take down the device from the internet and before you forget. Always start from the zero trust model for these devices and obtain the right documentation for the systems before you're deploying, because assumptions do not always work. And it is also, it should not be just secure design and implementation for any grid or other ICS related model, but also having correct incident response capabilities in place is equally important to defend from live attacks. We cannot be just like we have our PCI compliance, we have our all the checklist ready, and we are good to go. But we also need to be prepared, because when the right time comes, we need to fight back the attackers from using incident response. So with all this in mind, I hope that there were lessons learned from many angles, and you won't fall in any of these categories. So feel free to DM me on Twitter. DMs are open. You can follow my GitHub. Stay safe. Thank you very much.